in my last video I discussed about the energy states for an isolated atom, but right now I will discuss about the energy states for interacting atoms within solid. So I will start my discussion with two interacting atoms. Suppose this is one silicon atom who is interacting with another silicon atom, and of course if they are interacting with each other within a solid, then they have formed a covalent bond with the help of electron sharing. And these are the 4 valence electrons for this silicon atom, and these are the 4 valence electrons for this silicon atom, and the distance between the two nucleus should be less than 5 to 7 angstrom. This is the criteria. And their outermost shells are getting overlapped because of this electron sharing. So if I talk about the forces acting on this electron, then in case of isolated atom, the electrons in the outermost shell was experiencing a single attractive force by one single nucleus, but this time this electron is getting pulled by these two nucleus of these both of these atoms. So as a result, the electron changes its position, and the energy of electron will differ. Why so? Because in case of isolated atom, the electron was experiencing a single force, but this time the electron is experiencing two forces. So of course the energy will also differ, and the electron will change its position. So as the electron is changing its position and it is in a new position right now, then there must be an extra energy state for it, because electron cannot lie between two energy states. So if it is changing its position and it is in a new position, then at that new position there must be an extra energy state for that electron. So the electron creates an extra energy state to move. So if I want to visualize, then I can draw in this way. In case of isolated atom, this was the valence shell, 3s and 3p. The 3 was holding 2 electrons and 3p was holding 2 electrons. But in case of two interacting atoms, as the electrons are not in their places, the 3p gets splitted, and it gets splitted into two energy states, two different energy states, and these two electrons are situated in these two different energy states. But if I talk about a solid crystal, then obviously there is not two atoms are not there. There must be millions and millions of atoms which are present in that solid crystal. So as we are only dealing with these two atoms here, this valence shell is getting splitted into two energy states. But if I am talking about millions and millions of atoms which are present in a solid crystal, then there must be millions of energy states which are slightly differ from each other, and each of the energy state will be having an electron. So in our practical case, when we deal with a solid crystal, then we don't talk about energy states, we talk about energy bands. So if I want to define what is energy band, then I will say energy band is closely spaced discrete energy states. So before going to the energy bands, I want to show you something. I want to calculate how many number of atoms are there within a unit volume of silicon crystal, so that we have an idea that in an energy band there are how many number of energy states are there within an energy band. So I have told you that within a silicon crystal there are millions of atoms, but now we will try to calculate the exact number of atoms which are present within a unit volume of silicon crystal. So I'm giving the heading that calculation of atom in unit volume of silicon crystal. So if I talk about the silicon crystal, we first know about the structure of the silicon crystal. So it follows, the simple cubic structure. What is simple cubic structure? That means the unit cell of silicon crystal looks like this. looks like this. As you can see, this is 1/8 of a sphere. It looks like something like that. This is the upper surface. This is our front surface. This is the inner surface of the spheres. So this is actually the simple cubic structure that is followed by the silicon crystal lattice. So if it is an atom and this is an atom of silicon, this is one atom of silicon, this is one atom of silicon, then the distance between the nucleus, as we have discussed earlier, it is almost 5 Armstrong. So this is one nucleus of the silicon atom and this is one nucleus of the silicon atom. So this distance will also be 5 Armstrong, and the height of this cube is also 5 Armstrong. So the volume of the cube is equal to 5 Armstrong into 5 Armstrong into 5 Armstrong. So it is 125 Armstrong cube, which is 125 into 10 to the power minus 30 meter cube. That means 125 into 10 to the power minus 24 centimeter cube. That means the number of atoms per unit volume is equal to 1 by 125 into 10 to the power minus 24 cube. So if I calculate this, then the number becomes, okay, see, number of electrons per unit volume, which is, sorry, number of atoms per unit volume is equal to 0.8 into 10 to the power 22. That means it is more or less equal to 10 to the power 22 ms cube. So it means within and unit volume of silicon crystal, there are almost 10 to the power 22 atoms. So you can imagine, and within a unit volume of silicon crystal there are enormous number of atoms present. So that means, of course, the 3s and 3p shells, subcells, will split into enormous number of energy states. Like this. But of course the 2p, 2s and 1s, they will not get splitted because they are not the outermost shell. If the two atoms are interacting with each other, their outermost shells are getting overlapped, because but their inner shells are intact, because they are so that is the reason why 2p, 2s and 1s, they will not get splitted, but as their outer shell is overlapped with each other, that is why the 3s and 3p, both of this subshell will get splitted into into a huge number of energy states. So right now we are going to understand the concept, the origin of energy bands. So suppose, let's forget about this 10 to the power 22 atoms. Suppose I have n number of electrons in unit volume of a semiconductor. But we know that each of the each of the atom of any semiconductor is having 4 electrons in their valence shells. So if there are n number of atoms in unit volume of a semiconductor, then there must be 4n number of valence electron present in unit volume. So as we have calculated that within unit volume there must be almost 10 to the power 22 atoms of silicon in silicon solid crystal, then there must be 4 into 10 to the power 22 number of valence electrons present in unit volume. Then of course if I consider about a unit volume, then this 3s and 3p should get splitted into 4 into 10 to the power 22 number of energy states, because there are 4 into 10 to the power 22 number of electrons, and each of the electrons are having different uh, energies. They are experiencing different forces, so they will be having different positions and different energies. So for each of those electrons there must be empty energy state present. So that is why for this 4 into 10 to the power 22 number of valence electron, there must be a 4 into 10 to the power 22 number of energy states. So this valence shell will get splitted into this number of energy states, which are slightly different from each other. So of course this will form a very, what can I say, closely spaced discrete energy states, which means energy band. So I'm repeating it once again. We have calculated the number of atoms per unit volume, that is almost 10 to the power 22, but each of the atom of semiconductor is having 4 number of valence electrons in their outermost shell. So if we have n number of atoms in unit volume of semiconductor, then there must be 4n number of valence electron present in the unit volume. So if we have calculated that 10 to the power 22 number of atoms should be present within silicon unit volume of silicon crystal, then there must be 4 into 10 to the power 22 number of valence electron should be present within the unit volume of silicon crystal. So for this 4 into 10 to the power 22 number of electrons, the energy outer shell of atom should get splitted into 4 into 10 to the power 22 number of energy states, because each and every electron of the crystal is feeling different kind of energy and feeling different forces in different directions. So they all will be having their unique energy, and for each of the electron there must be some unique energy state where the electron can move. So the outermost shell will get splitted into this number of electrons to give space each and every electron present within that crystal. So that is why we are getting this 4 into 10 to the power 22 number of closely spaced discrete energy states, and we call it as energy band. So now we will be going deeper into this energy band. So up to this, I guess everything is clear. Now we will try to draw the band diagram. So this is the energy axis which we measure in electron volt, and this is the x is interatomic distance. Watch this very carefully, because this is the basic concept of energy band, and it is very important because energy band will be used for discussion of semiconductors, for discussion for discussing the energy of electrons within the semiconductor. Even it will be discussed further in BJT, MOSFET, JFET also, because we will deal with the energy of electrons in each of the electronic devices. So this is very important to understand the energy band and the position of the electrons within the energy bands. very very seriously. We need to understand this. So if we talk about the interatomic distance, we will point out this is our 5 Armstrong, this is our 10 Armstrong, and all these values are in centimeter. So right now if we draw the energy states of an isolated atom, that is, this is 1s2, this is 2s2, this is 2p6, this is 3s2, this is 3p2. Now listen, as the interatomic distance is large in this part, I mean from 10 Armstrong to infinity, the interatomic distance is large, so the atoms are not interacting with each other. So as they are not interacting with each other, then the electrons of their outer shells are not experiencing any external forces. All the atoms are behaving like an isolated atom. So there is no splitting of energy states. So as there is no splitting of energy states, there is no existence of energy bands. But if we decrease the interatomic distance, that means if we make the atoms come closer to each other, then what happens? That is the interesting thing. That is the most interesting thing about energy bands. So up to 10 Armstrong, everything is just as it is in case of isolated atom. But when the distance between the atoms comes near 10 Armstrong, then the 3s2 and 3p2, these two shell get splitted into different energy states. But remember one thing, 2p, 2s and 1s, they are never going to get splitted because they are not the outer shells. They are not getting overlapped with another outer shell of another atom. Only this n equal to 3, the outermost shell, that is only getting overlapped with the other outer shell of another atom. So only 3p and 3s, these two subshell will get splitted, and it will look like this. When the distance becomes less than 10 Armstrong, then it gets splitted like that, and this 3s gets splitted like this. Now you can see that 3p is getting splitted and it it comes within the splitting of 3s. So suppose there are n number of atoms within a unit volume, so there must be 4n number of electrons within the unit volume, because each one of the atom will be having 4 valence electrons, which I was talking a little bit earlier. So if there are 4n number of electrons, so this 3p and 3s will get splitted, and all these 4n number of electrons will get placed within the energy states in this bands. But 3p can hold 6n number of electrons, because each of the 3p subshell have the capacity of holding 6 electrons. So for n number of atoms, it can hold 6n number of electrons, 3p, and 3s can hold 2n number of electrons. So this combine, if we combine this 3p and 3s, it can hold 8n number of electrons in this combined fashion. But there are only 4n number of electrons are present, but they have the capacity to hold 8n number of electrons within this band, but we have only 4n number of electrons. So here also we need to remember the Pauli's principle, that electron will also electrons will always start filling from the lowest energy states. This is the principle, that the electron will always start filling from the lowest energy states. So of course, if if I combine this 3p and 3s, there must be 8n number of energy states within this band, but we have only 4n number of electrons present. So of course, out of this 8n, 4n will be occupied by electrons, and 4n states will not get occupied by electrons, and they will remain unoccupied. So which n number of states will get filled by electron, that is determined by this principle, that electron will always start filling up the energy states from the lowest energy states. So of course, if I talk about the variation of energy with respect to interatomic distance, so this at first these 3p and 3s will get combined with each other, then they will be splitted like this. Four n number of energy state will be in the lower band, and 4n number of energy states will be in the upper band, and this 4n number of energy state will be occupied by the electrons, because as you know that electron will start filling up the energy states from the lowest energy state. So this is the lowest energy state, and electron will start filling up, and it will stop here because all the 4n number of energy states in this band will get occupied by the electrons, by the exactly 4n number of electrons, but the energy states, the 4n number of energy states which are situated in this upper band, they will remain unoccupied. So if we talk about this band, this is actually the VB, or we say valence band. And if we talk about this band, this unoccupied band, this is known as CB, or you can say conduction band. And the difference between this lowest energy state of conduction band and the highest energy state of valence band, this is known as the forbidden energy gap. Forbidden energy gap. The lowest energy state of conduction band is denoted by EC, and the highest energy state in valence band is denoted by EV. So this forbidden energy gap is denoted by EG, that is equal to nothing but EC minus EV. So the difference between the lowest energy state of conduction band and the highest energy state of valence band is the forbidden energy gap. So of course we can see that no electron can present within this forbidden energy gap, because in a combined way, we can say if we combine 3p and 3s, then there must be a capacity of holding 8n number of electrons within a unit volume of silicon atom, silicon crystal. But we have only 4n number of electrons present in our hand. So, and as Pauli says, the electron will be occupying the energy states from the lowest energy states available. So it will at first fill up all the lower energy states, all these 4n number of lower energy states, and rest 4n number of energy states will remain unoccupied by the electrons. And the difference between the lowest state from the conduction band and the highest state of the valence band is actually known by the forbidden energy gap, and that is defined as Eg equal to Ec minus Ep, and no electron can reside in this forbidden energy gap. And in case of if there is no any external force that is applied on the semiconductor, external force is you can say doping, increment in temperature, or any external electric field. If any external factor is applied on the silicon crystal, then we can see this scenario. If we increase the temperature or any external electric force, or if we do doping, then we can see the electrons can go from valence band to the conduction band. That is the, I mean, the I will discuss all those things in the later version of our course. But right now, this is the ideal scenario when there is no external force or any external factor is applied on the semiconductor. The semiconductor is in an equilibrium state. Then we can see this scenario. All the all the energy states within the conduction band, they are unoccupied, and all the energy states within the valence band, they are all occupied by the electrons. And the difference between the splitting of the energy bands is actually the forbidden energy gap. And in case of silicon, the and at 0K temperature, the value of forbidden energy gap is 1.21 electron volt. So this is actually the origin of the energy band. So I guess everything is clear up to this, because at first I started with the analysis of two interacting atoms. Then I calculated how many number of atoms are present within a unit volume of semiconductor. Then I bring the concept of the energy bands from there, and then I told you about the splitting of the energy states, and then I told you about the conduction band, valence band, and the forbidden energy gap. So this is all I wanted to discuss about the energy bands in this lecture. And so if you have any doubt regarding this, you can ask me in the comment section. I will definitely try to make you understand